So in this part, we're going to go over one type of ODE that we can solve explicitly. And this is probably the most complicated equation we're going to solve explicitly. And even that, not for long, because you'll see most of the stuff we're going to be interested in doing doesn't actually require the explicit solution of an ODE. But because many first-order ODEs that we will encounter in this class are of this form, this linear form, let's actually go over one example on how this works. Okay, so a first-order linear ODE has this format. By the way, again, for more details, you can go on the main course of differential equation. There's a video lecture on that goes through more details. Here I'm going to just focus on the formula for solving it. Once you write your equation in this form, so y, remember, is a dependent variable, y denotes y of t, and the coefficient of y could be a function of t or a constant, and then the right-hand side could be a function of t as well, or a constant. When we say a function of t, we also include constants. So one can prove that the general solution is in terms of two integrals, which you have to do in this order precisely, because the second depends on the first. So the first integral is the integral of a of t dt. I'm going to call that big A of t. And the second one is the integral of the right-hand side times e to the big A of t. And then once you compute these integrals, the solution can be written in this form. And you'll see actually later that it's better maybe to write it without the parentheses, because the second term can be often simplified to look nicer. I usually give it in that form because it's easier to memorize if you have to memorize it. But if you want to write it nicely in a simplified form, most of the time this is a better way to do it without the parentheses. So let's take a look at the textbook example that doesn't have anything to do with the math biology. And then I'm going to comment on the typical equation of this type in math biology. So let's say we have y prime plus 1 over t, y equals t. Then according to my notation, little a of t is 1 of t, 1 over t, and little b of t is t. So big A of t is just the integral of 1 over t dt, which gives me natural log of t. And let's say we're looking for just positive time values, so that I don't have to worry about the absolute value here in the antiderivative. And I forgot to mention here that c is a constant of integration, which will always be determined at the end from the initial condition. All the models will have some initial condition to begin with. So a of t is ln of t, and then b of t is the integral of little b of t, which is t in my case, times e to the a of t, which is e to the ln of t dt. We can cancel e with the ln, and so b of t becomes the integral of t squared dt, which is 1/3 t to the power 3. By the way, I should have mentioned, when you go over these videos, pause most of the time when you try to catch up, because I'm assuming you do that, and that's why I don't take too many breaks when I go through the topics. Whenever you need the break, you have a pause button, which you can use in this format. So the full solution then, y of t is c e to the minus at, so a of t is ln of t, plus e to the minus ln of t times b of t, which is 1/3 t3. Now e to the minus ln of t, if you bring the minus inside, is 1 over t. So it's actually, because remember, minus ln of t is the same thing as ln of t to the negative 1. So when you exponentiate, e to the minus ln of t becomes t to the negative 1. So it's actually c over t plus 1 over t 1/3 t3. Simplify further, t3 with 3, c over t plus t squared over 3. Those of you who took differential equations remember maybe problems like this. And you also remember, again, something which will become crucial in our course, initial conditions, always. So we always deal in, when we have a model, when we have a population models, we don't just have an ODE like this, but you have some sort of initial conditions, usually at time 0. Now, in this particular example of mine, I can't have 0 for the time t. This is not defined at 0. So let's say you have y of 1 equals 1, one of the initial conditions. But whatever the initial condition is, you use that at the end to plug it in, that initial time, into the full solution. So c over 1 plus 1 squared over 3, and actually solve for the constant of integration. So in my case, 2 over 3. So the solution to what we call an initial value problem, which is just an ODE together with an initial conditions, is in my case 2 over 3 times 1 over t plus t squared over 3. Like I said before, we're not going to deal with this for too often because we don't deal with textbook examples. We deal with examples that have a meaning in population dynamics, or to be more precise, in infectious disease models. Later on in the notes, those of you who take the course right now, you noticed an example which is basically kind of similar to the exponential example, but with some modification, basically. A simple population model in which one of the positive contribution in the model, so the positive input in the population, is a constant, and the output, which you can call it the death rate, is given as per capita death rate. So I want to go over this example again. It's on the notes as well, but I want to go over it again to see how this works in the context of this formula that we talked about. Because one of the challenges, look, let me write again the standard way for the first order ODE. One of the challenges is that you have to adapt the problem at hand to some sort of framework that you know before, like in this case, the solution of a first order ODE. So the model I was talking about, for instance, is dp/dt equals k minus mu times p. So this could be basically a population model. P of t is a population at time t. Kind of messy here. Population at time t. Mu could be the death rate, so given as per capita death rate, which is the reason is multiplied by p, and k is a constant. Sometimes in the models this is called recruitment rate. It's just basically a fancy way of saying that you assume that in the conditions of this model, per unit of time, you have basically a constant number of people coming in. This sometimes is kind of an oversimplification, to be honest with you, because, for example, if you want to call it birth, that should be also proportional to the population. But you can also imagine, for instance, that it's some sort of small closed community in which it kind of averages out in the sense that the people coming in, either by birth or by other means, they are constant per unit of time. Or maybe you ignore births altogether and essentially pretty much have an average essentially of how many people come in the population. So if it's rather the same number from time to time, whatever the time unit is, from year to year or day to day and so on, you could assume that that input is a constant. But this brings back to what I said in the previous part. Always make sure you understand what stands for a constant and what stands for a function of t. So k and mu are constants. And so, for example, if I want to use this framework to solve this ODE, I have to write it in this form, which means y of t is replaced by p. So I'm going to have dp dt or p prime on the left side, but then move mu times p on the left and leave k on the right hand side. So it's important to understand that now a of t and b of t are constants. They are denoted by letters, but they are constant nonetheless. So this is what I'm talking about, that the math actually is not that difficult, but it could be confusing before you get used to the notation. It's not difficult because dealing with constants has got to be easier in terms of integrating this equation. So if we follow the framework from the previous part, a of t is the integral of mu dt. That's just a constant, so that's just mu times t. And b of t is the integral of b of t, which is a constant k, e times a of t, which is e to the mu t. This is like me integrating, let's say, 5 e to the 3t. It's very easy to integrate. It's pull the constant out. And how do you integrate it to the 3t? If you want a number in mind, that will be 1/3 to the 3t. That's just going to be 1 over mu e to the mu t. So lots of symbols, but if they're constants, things are not that bad. And then, of course, p of t, the full solution would be e to the minus a of t, some constant of integration plus b of t, which is k over mu e to the mu t. And let's write this same thing without parentheses. If we multiply and simplify, you get this. And remember, there's also always an initial condition, and in modeling work, this is denoted by P naught, or if you have an actual number of people to begin with, you could use that. So that's the initial population, which will give you the value of this constant. So now you plug in the time 0 for t, and the constant of integration becomes p naught minus k over mu. So go slow, because I know it looks more complicated than it is in reality. So let's write the full solution. Constant e to the minus mu t plus k over mu. So I know that it looks more complicated than it is in reality. The reason I'm saying that, because I want to insist it's not that as complicated, is because, again, these are actual numbers. If most people could do differential equations, if you were to give actual numbers here, then this will be much, much less tedious, right? Because this will be just an actual number, not an expression like this in terms of the initial condition. Now, fortunately, for most of the questions we have to address, we don't actually need to solve these equations. I'm going to talk about that more on the third part. But even now, on looking at this, I want to insist on the importance of keeping these generic variables and parameters in the model and not actually use actual numbers to get some insight. Because, for example, let's say this is your model, right? What do you do with it, right? I mean, at the very least, you try to predict something. Now, this is such a basic model, pretty much the only question I could ask is, what is the limit of p of t, right? I mean, as p of t, as t goes to infinity. So let's say in this case, it's pretty obvious that even if I use actual numbers, it's pretty obvious that the limit exists, first of all, right? That, the limit goes to k over mu, I mean to a constant, because e to the minus mu t goes to 0. But what does the limit mean in terms of the original parameters? See, this will be lost if this will be an actual number. If I have here whatever the k over mu is, you may not know that the value of the limit actually is related to the ratio between k over mu. So the limit is k over mu, but in the language of math biology is basically the ratio of recruitment rate and death rate. Now, there's a very good reason why that's the case, which we'll learn later. We're going to learn what one over mu means and so on and so forth. But I want to point out again that this is why we keep variables in the model, right? I mean, we have to relate the result with the parameters that mean something in real world. A number is just a number, but what does it mean in terms of the original parameters? Even this constant is important if you think about. Because, for example, maybe you want to ask more about the model, not just what the limit of P of t is. Maybe you want to ask, does the population increase or decrease, starting with a certain population value? Now, with calculus 1 methods, and with much faster method we're going to learn later, but with calc 1 method, if I found the solution already, to figure out if the population increases or decreases, all I have to do is to take the derivative and see if it's positive or negative. Let's see, if I take the derivative, then it's going to be P naught minus K over mu, differentiate this with the chain rule, and then K over mu is a constant, so that's going to be 0. Okay, so all these parameters are positive because they denote biological rates, population, recruitment rate, death rate. So there's a minus here. So notice that if the initial population is less than K over mu, then I'm going to have this guy negative times negative. That makes it positive. So that means P prime is greater than 0, P increases. And if P naught is greater than K over mu, well, the sign will be opposite, right? So therefore, P prime, P will decrease. That could be important in your modeling work, right? Because you could predict more about what happens with the population depending on whether the initial population size is. So depending on the relation between the initial population size with some other important term in the model. So in the notes, you have a graph of this, and you will see how the solution approaches asymptotically K over mu. Which means that this K over mu acts like some sort of carrying capacity, which is basically the final population, the kind of the long-term population size, if you want. Okay, I mean, in the sense that if you're above it, you go down toward it. And if you are below it, you will approach it as t goes to infinity. So it's kind of the overall limit of the population. So with that in mind, we're going to move on to the third part, in which I'm going to comment more on how you actually get these insights, these modeling questions answered without in fact solving explicitly for the population. So stay tuned.